Yeah, so in this lecture, we will talk about unconstrained optimization. Just a very brief review of what we did last time. We talked about convex sets and convex functions in the previous lecture, especially their properties. Right? First, give the definition of what is convex set, what is convex functions, and then we give you a few examples. And then what's important in the previous lecture is we give the first order characterization of the convex function. That means if you do take a point in a convex function and then take the derivative, right? The derivative and the slope will under approximate the convex function. We also give the second order characterization of convex function. We know that the Hessian of any convex function is positive semi-definite. And then with these properties, you can prove whether a function is convex or not. And also we gave several sort of operations that preserve the convexity of functions and operations that preserve the convexity of sets. Right? So throughout this class, you will realize that in order to design optimization algorithm to solve a particular problem, we first need to understand the property of the problem you are solving. Right? So like in the previous lecture, we first understand the properties of convex functions and convex sets. Then with these properties, you can design algorithm to solve those problems. Right? So you will see that we will follow this sequence in this class. Like, let's say if you move to more complicated problem, let's say linear programming where you have linear objective and linear constraint, right? So in that case, we will also first study the property of the linear programming, like what is the properties of this polyhedral set. Then we will design algorithm to solve this problem. Okay, so since last lecture, we already understand the properties of convex functions. It is straightforward to design an algorithm that solve a problem with objective as a convex function. Let's assume minimize x, f of x. F is convex and differentiable, where the domain of f is assumed to be Rn, right? Meaning that there are no constraints in this problem. Right? So this is a simplest convex optimization problem you can think about, right? So now we denote the optimal value by f star and the optimal solution by x star. So this is a problem we will consider in this lecture. Okay, so first of all, let's prove an important property. We already alluded that in the previous lecture, but we did not give a rigorous proof. Right? So to motivate the introduction of convex function, we said one important property of convex function is that any local minimum is global minimum, right? So that's why convex optimization is easy to solve. Okay, so how do we prove this property? Okay, so again, the statement is any local minimum is global minimum, right? So any thoughts how we can prove this type of property?
Contradiction that there is no any other minimum.
Okay, yeah.
By assuming that there is another minimum,
yeah.
which is global.
Right, exactly, right. So you could do something like prove by contradiction. So let's assume we have a local minimum point, right? So let's assume we have a point, let's call it x star, is a local minimum right? So what is the definition of local minimum? If you remember in the previous lecture, we used this epsilon delta way of describing the local minimum, right? So that means if x star is a local minimum, there exists, maybe let's just use delta here. There is a delta greater than or equal to 0. Then for all the x that are close enough to x star, we have f of x greater than or equal to fx star, right? So that's the definition of a local minimum. Then what remains to be seen is that if x star is a local minimum, then this is what we want to show, right? For any y, let's pick an arbitrary y, we have fy greater than or equal to fx star, right? So this is what we want to show, okay? And then the other property we have is f is a convex function, right? So if f is a convex function, we can sort of so you could draw a picture, something like x star. When x star is when y is close enough to x star, let's say in this ball with length delta, x star is a local minimum. And then if you pick any arbitrary y, we want to show that y has to be greater than or equal to fx star as well. So intuitively, you would want to use the convexity property. Right? So by convexity, what you can show is, let's say you have, maybe let's pick delta. Delta is a small enough number. Then we have f1 minus delta x star plus delta times y is less than or equal to 1 minus delta f x star plus delta f of y, right? Okay, so this is a convexity property, right? If delta is a small enough number, you can assume delta is between 0 and 1. If delta is not between 0 and 1, let's say delta is too big, you can always pick a smaller delta between 0 and 1, right? Yeah, so here you use this convexity property and write it down, apply it to x star and y, right? So then we could further use some argument here where you see when, so maybe I shouldn't be using delta here. So let's use another letter. So let's use maybe epsilon here. Okay, so now, we know that when epsilon is small enough, right? This point will be in this ball with length delta, right? So there exists epsilon small enough right? When epsilon is not small enough, this point is arbitrarily close to x star, right? So it will be in this ball here. We have f1 minus epsilon x star plus epsilon y, let's say, minus f of x star. So we can minus fx star on both sides of the inequality, and then on the right-hand side we get epsilon fy minus fx star. Right, so here I did nothing but just deduct both sides of the inequality by fx star, right? So we know that this point is greater than or equal to 0, because when epsilon is small enough, this point is arbitrarily close to x star. So since x star is a local minimum, then we know that the difference is greater than or equal to 0. Okay, so that's the trick we did here. Then we have Fy is Fy minus x is greater than equal to 0, right? Epsilon is a number that is greater than 0. Then we conclude Fy is greater than equal to Fx star, right? So here, y is chosen arbitrarily, right? So here without loss of generality, we have shown that Fx star is a global minimum. Okay. Again, to summarize what we did, if x is a local minimum, we know that there exists a neighborhood of x star. For all the f of x in this ball here, fx star is a minimum, right? And then we take the convex combination of x star and any arbitrary y here, right? So if we pick the epsilon, where epsilon is a very small number, then it will fall into this convex combination will fall into this ball. Therefore, this point will be greater than fx star, right? So with that, after some algebra, you can show without a loss of generality, Fy must be greater than or equal to Fx star. Okay, yes?
So for convex function, can we say that there is only one local minimum or global? Because
for an unconstrained convex function,
Well,
not necessarily.
if you mean the value, it can be like a line and you can have multiple x's.
Yeah, so
But
yeah.
if you mean the
So
f star,
so the optimal value is unique, right? Of course, the global minimum is unique, but there can be multiple x that achieve the same minimum, right? So that's draw an arbitrary function, which is convex. So let's say you have a convex function like that looks like this, right? So now everything on this line segment is a global minimum.
so for strongly convex.
Yeah, for strongly convex, that is the case.
Okay.
Yeah. So if you have a strongly convex where the Hessian is positive definite, then there is a unique minimum. I think so. You can try to show that. Okay, so this is basically the short proof. Now, after showing that, there is another property we will be using to get the minimum of a convex function. So the theorem is saying the following. For a differentiable convex function f, a point x star is a local, or since any local minimum is a global minimum for convex functions, then we say x star is a global minimum if and only if the gradient at x star equals to 0. Okay, so this gives you a necessary and sufficient condition to get the global minimum for convex functions. So how do we show this is true? Maybe let's say for the one direction, right? So if we have f is convex and differentiable, then x star is a local minimum. Right, so if this holds, we want to show that the gradient at x star equals to 0, right? Any ideas on how to show this? So, or maybe in other words, what will be the strategy we will be using to show this?
Contradiction.
Yeah, exactly, right? How do you use contradiction? So let's assume if the gradient is non-zero, we want to show that x star will not be a local minimum, right? Okay, so why, if the gradient is non-zero, x star will not be a local minimum.
Well, it means if we move in the direction where the gradient is in the opposite direction of the gradient, then the value will decrease.
Yeah, exactly, right. So that's sort of the intuition. So if you want to show that rigorously, you can use things like mean value theorem, right? So if the gradient at x star is, so by contradiction, if it's non-zero, you can move in, let's say, negative fx star direction. And then you can decrease the function value, right? Okay, what about the other direction? If the gradient is 0, we want to show that x star is a local minimum or a global minimum. Any thoughts? So just a hint here, we will be using the first order characterization of convex function, right? So remember, the first order characterization of convex function is saying that if you take the gradient at point x star to approximate the function f of y, right? It will always under approximate the function of f y, right? So if the gradient is 0 here, right? So it will essentially zero out the second term, right? So using the first order characterization, we know that for any arbitrary y, fy will always be greater than fx star, right? So this is a very strong property that shows x star is a global minimum. Okay. Yeah. Okay, so let's absorb this a little bit, then I have a question for you. All right, so now my question is, if f of x is a differentiable and continuous function, but it may not be convex, and I have the gradient of f of x equals to 0, right? So now the question is x star a local minimum, right? Because it's not a convex function, of course, it may not be a global minimum, right? So let's say if f is differentiable and continuously differentiable, right? And the gradient at x star is 0, right? So is x star a local minimum?
No.
Why is that?
Saddle, it can be saddle point.
Yeah, exactly, right. Can you give maybe a counterexample?
X cube.
Yeah, exactly, right, x cubed. So if f, let's say, is non-convex, right? So fx star equals to 0 does not imply local minimum. Right. So a counter example would be f of x equals to x cubed. Right. At x equals to 0, we have the gradient, in this case the derivative, equals to 2x equals to 0. Right? X equals to 0 is not a local minimum, right? Because you perturb it a little bit to the negative direction, it will go negative. Right? So it is a saddle point, is exactly as Sergey said. Okay. Yeah, so this is a quick proof of the optimality condition. So we will be using this optimality condition to design an algorithm such that we can get the local minimum for a convex function. So here we will restrict our attention to convex functions. We won't worry too much about non-convex function. Right? So if you want to think about how do you solve a non-convex optimization problem to local minimum, then there is another set of methods. Right? Of course, you can use the gradient-based method as sort of like a heuristic. Okay, so the method we will be using is called gradient descent. Right? Even if you haven't taken optimization class before, you might have already heard about gradient descent. Right? The idea is it is an iterative method used to find the minimum of the function. Right? The idea is to say we will move in the direction of the negative gradient. Right? You guys already told me that if you have the gradient being non-zero, you can always move to the negative gradient direction. Right? So if you move to the negative gradient direction, you can always get a decrease in the function value. Right? If the step size is small enough. Right? So here the idea is the following. Right? We will have an iterative algorithm where we denote the x value at iteration k as x sub k. And we move in the direction of the negative gradient. And this number tk is called step size of the gradient descent, right? Meaning that how long a step you are taking using the negative gradient direction. So for those of you who are more familiar with machine learning than optimization, you probably heard this term called learning rate. Right? So if you, let's say, you use a commonly used machine learning framework like PyTorch or TensorFlow, right, to train neural networks, then you can specify a parameter called learning rate. Right? The learning rate is pretty much the step size you use in gradient descent. Okay. And the choice of the step size is crucial for gradient descent to converge. Okay. And under certain conditions, gradient descent converges to a local minimum, right, which is global if f is convex. Right? So here we will only discuss the convex case. Yeah. So first of all, let's show a sort of interpretation of gradient descent. Right? Why do we take the negative gradient direction? The reason is the negative gradient direction is so-called steepest descent direction. Right? So why do we see that? The reason is you assume f is differentiable, right? And the gradient at f is denoted as this notation here. So if you take the directional derivative f in the direction of a unit vector u, right? Let's suppose you can take different directions at a given point x, then the directional derivative is given by the inner product of the gradient and this vector u, right? Okay, you can take any arbitrary direction u, right? So let's assume if u is a unit vector, right? And if you want the directional derivative to be as negative as possible because you want to decrease the function value, then you would choose u to be the opposite direction as a gradient. Right? So that's why it is called a steepest descent direction. Right? It is a direction that gives you the most negative directional derivative. Right? Okay. So now after stating this property, let me ask you the following question that may confuse you or maybe help you understand this steepest descent property better. Right? So supposedly, I gave you so let's suppose I give you a direction vector with length less than equal to, let's say I give you an arbitrary number with slightly abusive notation, tk, right? So suppose at a given point x, I tell you you can take any vector as the next step whose length is smaller than or equal to a scalar tk, right? Now, is the following claim true? The vk that give you the most descent is a negative gradient direction. Again, so the claim is the following. I'm at a given point xk, okay? Now, I'm trying to decide the direction vk, right? The only constraint on vk is that its length has to be smaller than equal to tk, okay? You can take any arbitrary vector or arbitrary step whose length is less than equal to tk. My goal is I want to find vk such that I can minimize the function value after taking the step vk. Okay. So now the question is, I'm trying to find the vector vk that minimizes the function value. Is this vk the same direction as a negative gradient direction?
Not necessarily.
Yeah, so why do it?
Well, because gradient is like first order approximation.
Yeah.
We have like a second, third, and so on.
Mm-hmm.
Like there's some curvature.
Yeah.
It could be a different point,
Yeah.
which minimizes.
Yeah, exactly right. So it does not necessarily has to be the negative gradient direction, right? Because the negative gradient direction is a local property, right? It only says the negative gradient direction gives you the steepest descent at this particular point xk, right? If you move a little bit away from xk and take the gradient again, right, you are going to have a different direction, right? So therefore, if you have a finite size vector, which is non-zero size vector to choose from, you may not necessarily choose the negative gradient direction, right? Okay, so that's a key property I want to distinguish, because sometimes the steepest descent can be confusing, right? Because you may believe that no matter how far you go, you can just take the negative gradient direction, right? But it is not necessarily the case that it is a steepest descent direction only at this local point, xk, okay? Yeah, so now let's visualize this property a little bit, okay? So here I have the xk at a particular point, right? So those are the contour curves. I want to find minimum, which is in the center of this contour plot, okay? So you can take the gradient direction at this particular point, but the question is, you don't know how far you want to go, right? If you, let's say, go too far along this direction, you will overshoot, right? If you go take a very small step, you will take many iterations to go to the minimum point. Okay. Yeah. So now there is. Let me give you another interpretation of gradient descent. Right? So this is just a different interpretation. If you don't want a different interpretation, you can just remember you take the sort of the steepest descent step. So another way to interpret gradient descent is the following, right? Suppose we consider a Taylor series expansion at the particular point x. So that gives you this quadratic term where you need to use a Hessian of the function f. So now let's assume we don't want to calculate the Hessian. We just approximate the Hessian using an identity matrix. Okay. Now, if you replace the Hessian with an identity matrix, you will end up with this expression here. We have f of x plus the first order approximation, and then we have what is called a proximity term to x. Right? So this is essentially calculating distance between y and x, right? If you replace that with identity matrix. So the idea is we have this approximation, then the next point we pick will minimize this approximated expression, right? So that you can calculate the minimizer of this function. This is a strongly convex function because you have this quadratic term here, right? And then you can find out that the x that minimize this approximation is essentially the gradient descent direction. And this is just another way to interpret gradient descent. Okay, so now let's talk a little bit about how to choose step size. Right? As I said, if you choose a step size that is too long, you may overshoot. Okay, so this is a case in this plot here. Let's assume we start from this particular point here, and then if the step size t is too big, here I'm plotting this particular function. It is a quadratic function here. You can see that it will diverge after a few iterations because the step size you pick is too large, right? So that is also another empirical way to show you that if you take a finite step size, you cannot just naively think the steepest descent direction it will give you the minimum, right? Because the gradient is only valid at this particular point here. If you use this gradient for too long, it might even diverge. Okay. On the other hand, if you choose a step size that is too small, it will take too many iterations to converge, right? But on the other hand, you don't suffer from this divergent behavior because the step size is small. The gradient is still valid in the neighborhood at this point you calculate the gradient, right? So you are still taking a descent direction, but then you need many iterations to converge. Now, if you happen to pick a step size that is what is called just right, then you will converge within a small number of iterations, right? So this is why perhaps if you guys have run some sort of machine learning experiments to train deep neural networks, this learning rate or step size is what is called a hyperparameter you want to tune. Right? If you happen to get the right step size, you will have a model that gives you good accuracy. Right? So that is some parameter you want to tune. But tuning those parameters can be quite tedious. Right? In practice, most people use a method called backtracking line search. So what is a backtracking line search? You can think about this as a way of adaptively adjusting the step size, right? So as we said, the high-level idea is if the step size is too large, the gradient direction may not even be a good direction, right? You might even diverge. But then if the step size is too small, the gradient gives you a descent direction, right? But you are not really taking advantage of this gradient direction because you only make a very marginal move at the current point, right? So that's what rationale of this backtracking line search is. So here, you first pick some hyperparameters, alpha and beta. I will explain what alpha and beta means later on. So at each iteration, you start with a given step size. And while this condition is true, right? So this condition may look confusing in the first place. Let's try to interpret this condition a little bit. Okay, so here, the t is the step size, right? And this is a gradient direction. The idea is if this new point, right? So we are evaluating the function value at this new point by taking the gradient direction with step size t, right? So if this new point's function value is greater than the right-hand side, where we have the square of the gradient times t times alpha. Okay, so that means the new function value you got is even greater than the norm of the gradient, right? So as you know, if t is small enough, the decrease you got is a norm of the gradient. Why is that true? Okay, so let's say, consider this point here, f of x minus t So if you do the first order Taylor series expansion of this term, right, it is nothing but f of x minus t times the gradient transpose the gradient, right? Because you are taking the negative gradient direction, right? This is nothing but the first order Taylor series approximation, right? So this thing is, you can represent it as the norm, the two norm of the gradient, right? So when is this approximation accurate? It is accurate when this number t, or the step size, is very small, right? When the step size is small, this new point is very close to the point x, right? So you can use first order Taylor series approximation. So having said that, you know that when t is small enough, the decrease you get in the function value is roughly t times the norm of the gradient, right? Okay. But here, you choose the alpha value between 0 and 0.5, right? So that means, but here I don't have a 0.5, right? We have 1 times t times the norm of the gradient, right? So that means as t goes smaller and smaller, this decrease will always be smaller than the right-hand side, right? Because here you choose alpha between 0 and 0.5, right? So while it is not smaller than the norm of the gradient estimate, you will shrink the step size t. Right? That means you go too far from the current point, right? So this tends to work pretty well. Okay, so let's visualize this in a plot. Okay, so let's say we are currently at this point, right? So if t equals to 0, you just stay at this point, right? And we know that when t is small enough, then if you move towards the gradient direction, the decrease you get is roughly this first order approximation, right? So when as you can see, the function value roughly align with the gradient direction when t is small enough. But then when t is too big, then you are not getting this decrease in the gradient direction, right? Because the gradient is no longer a good approximate. But what we know we want to do in the backtracking line search is you want to get a decrease that is below this particular estimate here, where alpha is a number between 0 and 0.5. Right? So essentially, you want to get a direction that is below this particular curve here. Right? So that's sort of the rationale of backtracking line search.
Why is alpha between 0 and 0.5 and 5.5?
Yeah, so 0.5 is a heuristic they use. You can pick a bigger number, right? As long as it's not 1, right? If you pick 1, it may not be achieved, right? If you people have find out in practice, you pick some numbers between 0 and 0.5, right? 0.5 can always be achieved if t is small enough. Okay. Any other questions?
And when you shrink the shrink the step size, you can shrink it arbitrarily by choosing any number between 0 and 1.
When you shrink the step
Yeah.
size. Yeah. So you could always multiply this step size by beta, where beta is between 0 and 1, until this condition is satisfied. Okay, yeah. Right. So again, when if you choose a step size that is too large, let's say if you overshoot to this particular point, right, you don't get a decrease compared with this approximation, right? So if you are at this point, you are not getting enough decrease compared with this gradient estimate, then you will shrink the step size. Maybe you jump here, then you are below this line here. Okay. Yeah, so this is a sort of a backtracking example. In practice, this heuristic usually works pretty well. There is another method called exact line search. Right? Even backtracking line search is not exact. Right? So exact line search means when you use this gradient direction, you want to find the exact step size to minimize the function value. Right? So here, you choose step size s greater than or equal to 0 that minimize this function. Right? So this arcmin means you pick the s that minimize this particular function value and take the argument. Right? Of course, for most of the problems, exact line search will not be very efficient. Right? Unless for some special problem, you can get an exact analytical solution to this problem. Otherwise, you won't do exact line search, right? Because by itself, it is an optimization problem. Right? It will be computationally too expensive to do. Yeah. Now let's talk a little bit about convergence analysis. If you take a convex optimization class from, let's say, industrial engineering, most of the class will be about how to prove convergence, how to prove convergence rates, and so forth, right? If you do, let's say, research in convex optimization, the algorithm is usually very simple. If you look at most of even the state-of-the-art convex optimization algorithm for unconstrained problem, the algorithm is simple and also very simple to implement. But I would say probably over 90% of the time is spent on proving convergence on those theoretical properties, right? This is not my expertise since we are in engineering. Usually we care about computation more than the theoretical properties. But then if you are very into the theory of optimization, you will spend maybe 99% of the time on convergence analysis. But I do want to show you some result from gradient descent such that you are aware of this convergence order. Okay, this is just showing the result without giving a proof. So there are some result for gradient descent which says if the gradient is Lipschitz continuous, this is a so-called Lipschitz continuous property, then the gradient descent with fixed step size give you the following convergence order. Right? Where xk is the function value at iteration k, f star is the global minimum. And it can be, this is like the optimality gap, right? The function value you get at step k and the global minimum. And they can be bounded by the initial point, x0 minus the, of course you don't really know where the, how far you are from the global minimum, right? This is like a theoretical analysis, divided by 2 times t times k. So those constants may not matter that much. What really matters is the convergence rate, right? So all those big O notation. As you can see, the gradient descent has a convergence rate with respect to k as 1 over k. Right? So if you have, if you want to achieve epsilon optimum, in other words, you need around 1 over epsilon iterations. Okay, that's sort of the order of magnitude we have. Now I'm going to switch gears and talk a little bit about Newton's method, which uses second order information. Again, if you look at the gradient descent, it only uses first order information, or the gradient information, right? So Newton's method is what is called a second order method, where you assume the function is twice differentiable, where you will use the Hessian information. Okay. Just to recall, gradient descent is taking the gradient direction, or the negative gradient direction. The Newton's method is taking the gradient direction multiplied by the inverse of the Hessian. Right? So in other words, you can think about the direction as skewed by the inverse of the Hessian. Okay. Since you use second order information, this is called a second order method. Right? Now, you don't need to remember this update formula for the Newton's method. Every time you want to remember the Newton's method, you can derive it yourself. Right? So I will show you an easy derivation for Newton's method. Okay. So remember, in the first order method, we approximate the Hessian using the identity matrix. That's why we have this proximal term here. But then in the second order method, instead of approximating the Hessian by the identity matrix, what if you just use the Hessian itself, right? So this is nothing but a second order Taylor series expansion at the particular point. Right? So what if you want to find the minimum of this second order approximation, right? Since you know that for a convex function, the Hessian is positive semi-definite, right? So this approximation gives you a convex quadratic function, right? So this Hessian is positive semi-definite, therefore this whole term is a convex quadratic function. Now, if you want to find the minimum of this convex quadratic function, then you can take the derivative, set it to 0. Take the derivative with respect to y, set it to 0. Then we will find the minimum is achieved at exactly the Newton's formula. Right? The Newton's formula is inverse of the Hessian times the gradient. Okay, so that's sort of an interpretation of Newton's method. Now there is another way to interpret Newton's method using the idea of solving nonlinear equations. Okay. Recall that the optimality condition for convex optimization problem is saying we need to find a point such that the gradient equals to 0. Right? So maybe at the current point the gradient doesn't equal to 0. Then we want to find a direction v such that x plus v, the gradient at x plus v equal to 0. Right? So now what is this expression here? This expression has n equations and n unknowns. Right, the unknowns are the vector v. Right, so as standing at a particular point x, you want to find the direction v such that the gradient equals to 0. Right? You have n equations and n unknowns, but the n equations may be nonlinear. Right? So how to solve nonlinear equations? Right? If you have taken a class on numerical analysis, there is a method called Newton's method to solve nonlinear equations. Right? So how does that work? The way it works is you can consider a first-order approximation of this nonlinear equation. Right? So the nonlinear equation equals to 0, so let's denote capital F as the systems of nonlinear equation. Right? So you can approximate this nonlinear equation by the function value evaluated at x plus the Jacobian times the perturbation vector v. Right? Okay, and you can set this first order approximation to 0, which use exactly the Newton's direction. Okay, so the Jacobian here is actually the Hessian, right? Because here you are already taking the first order derivative. The Jacobian is taking the derivative of this nonlinear equation, then you got the Hessian. They are the same thing. And this work was proposed by Newton and Ramphson, right? Originally on finding the roots of polynomials. Actually, of course, you can imagine solving nonlinear equations is a more basic problem than optimization problems, right? So you can think about Newton's method as an application of Newton's method to nonlinear equations, right? Yeah. So if you want to visualize Newton's method for solving nonlinear equations, right? So let's assume we are in a one-dimensional case, right? I'm trying to find the root of this blue curve here, right? Suppose I'm at this particular point here. Then what I can do is I calculate the slope at this curve, right? And then I intersect the slope with the x-axis, right? So this will be my next point. Okay, then you repeat this, right? So this gives you this function value here. Then you can calculate a slope again, right? Then it will hit this particular point. Then you repeat, right? As you can imagine, it will converge to the root of this nonlinear function. That's how roughly how Newton's method works. Okay, so now I've talked about the intuition of Newton's method, right? There are two ways to interpret that. One is just use a second-order Taylor series expansion and minimize that second-order Taylor series expansion. Right? You basically minimize a quadratic function, and then the Hessian is a positive semi-definite. Right? Then you can solve that quadratic function to give you the next step. The other way of interpreting that is solving nonlinear equations, set the gradient to 0, and use Newton's method to solve nonlinear equations. And there is one very interesting property of Newton's method called affine invariance. Right? So as you can imagine, let's see if you go to this picture here. Right? So if you are at this particular picture here, you might consider, you may want to scale the x1 and x2 variable. Right? Clearly, they are not of the same scale. Right? That's why you have this sort of elongated ellipsoid shape here, right? So if you scale the problem better, maybe this problem will have better convergence property, right? That's what is you want to do in gradient descent. But then one interesting property of Newton's method is it is not sensitive to scaling. Right? You don't really need to scale those x variables. Right? This is just a very simple proof that even if you scale the x variables using this matrix, non-singular square matrix A, you will still get exactly the same update. Right? So I'm not going to the details. This is nothing but going through the algebra. So the progress of Newton's method is independent of problem scaling. Right? So that is a very nice property to have. And you don't need to worry about scaling the x and y axis and so forth. But if you are using gradient descent, you have some very big numbers and some very small number. You better scale them to be in the similar order of magnitude. Okay. Now, so how do we know when will Newton's method converge? Okay. So typically, in the implementation, people use something called Newton decrement, which is the gradient multiplied by the inverse of the Hessian multiplied by the gradient, taking the square root of that. So you can think about this Newton's decrement as a way of measuring the gradient. Right? We know that as the gradient goes to 0, you are converging to the global minimum. Right? But instead of using the norm of the gradient itself, you can scale it by the inverse of the Hessian. Right? The inverse of a Hessian is also a PSD matrix. If the Hessian is PSD, the inverse of that matrix is also PSD. So then if you take the gradient transpose inverse Hessian, the gradient, this is a measurement of how far you are from the global minimum. Right? So why it is that is the case, you can sort of interpret it as the distance from fx and the minimum of this quadratic approximation. Right? So you can use this quadratic approximation as a way of approximating the global minimum. Right? And after some algebra, you can get this is just lambda of x. Right? So usually people use this lambda x squared as an approximate upper bound on the suboptimality of x. Okay. Yeah, and similarly in Newton's method, you can do backtracking line search. Right? I won't go to the details. The idea is very similar. Instead of taking the gradient direction, you are using this Newton's direction here, right? And similarly, this term is like a sufficient decrease term, right? Instead of taking the square of the gradient, you are replacing this with a first order approximation of the direction v. Okay. So what about convergence analysis? Again, if you want to take a whole semester class on convex optimization, probably this will be 2 or 3 lectures to prove the convergence of Newton's method. I will just show you the result to give you some intuition on how fast Newton's method converges, right? So the conclusion is the following. So Newton's method with backtracking line search satisfying a 2-stage convergence bounds, where K0 is the number of iterations where the gradient is still less than or equal to a number eta, where I'm not going to detail. You can think about eta as dependent on the convexity property on the Lipschitz property of the problem. So first of all, for the first K0 iterations, each iteration will decrease the function value by gamma times K, right? But what's more important is as you goes to the global minimum, how fast does that converge, right? So the issue with the first order method is usually it can converge pretty fast in the first few iterations. But if you want to get an optimality gap, let's say 10 to the minus 6, gradient-based algorithm usually struggle to converge as it gets closer to the global minimum, right? Because you have to pick very small step size as it gets close to the global minimum. But Newton's method sort of alleviates this property, as you can see, as a number iteration becomes large. This is a very fast convergence rate. You have exponential over exponential convergence rate. Okay, so it's a 1 over 2 raised to the power of 2 raised to the power k. Okay. Yeah, so that's sort of the things you gain by using a second order method. It has faster convergence rate than first order method. Okay. So let's compare a little bit about first order method and second order method, or maybe we could discuss a little bit when do you use first order methods, when do you use second order method. Okay. So first of all, let's consider the memory of storing those matrices. Right? If you use Newton's method, you must store the Hessian matrix, right? So you have an n by n matrix. And each gradient iteration only involves n-dimensional vector. Right? You only need to store the gradient. Okay, so therefore, of course, with respect to memory, second order method is more expensive. Okay. Now, the other thing we care about is computation, right? So memory has to do with your RAM. Computation has to do with your CPU, right? So each Newton's iteration requires n cubed flops operation, right? So you need to solve a n by n linear system, right? Okay, and each gradient iteration only requires on steps. Okay. Now, what about line search? Right? Yes.
So, how do we compute Hessian, and what's the order of computation? How does it?
Yeah. So let's say if you want to compute Hessian, you could use any either use numerical method or use symbolic method, right? So let's assume you need to compute an n by n Hessian, right? Then the order of computation is n squared, right? Right, because each item, let's assume computing a gradient only need let's say O1 operation. Okay, so then computing the Hessian will be n squared. But if you want to take the inverse of an n by n matrix, that will be n cubed, right? Since you need the inverse of the Hessian. Yeah, so matrix inverse is very expensive operation. Right, okay, yeah. I will make a comment on that later. Now, let's consider backtracking line search, right? Since you already fixed the search direction, each iteration of backtracking line search is an additional vector and evaluating the function value at that particular vector. Then the order is O(n). Okay. The final remark is conditioning, right? Or whether you need to scale the problem such that it has good conditioning or not. Gradient descent can have bad conditioning if you do not scale the problem very well. Newton's method does not have this problem because we show that Newton's method is affine invariant. You sort of scale the problem by the inverse of the hashing already. Okay. So when do you use first order method? When do you use second order method? Right? It is very clear if you evaluate the problem on a per iteration basis, Newton's method is much more expensive, right? It's n cubed, and the memory is n squared, right? And then first order method is O(n) on both memory and the computation, right? The advantage of Newton's method is that it has much better convergence properties, especially if you want to get good solution, right? Okay, so in summary, I would say that for smaller scale problem where you want good accurate solution close to the global minimum, then you will use second order method. That is a case for most engineering problem where the scale is not that large, right? And you can afford to take a matrix inverse. On the other hand, if the problem size is too large, then you will use first order method, right? Again, using deep learning or machine learning as an example, almost all the deep learning packages like PyTorch or TensorFlow uses first order methods. Okay, the reason is the scale of the problem is too large. If you think about models like those large language models, right? They could have tens of billions of parameters. That means the x variables dimension is hundreds of billion, right? So if you want to calculate the inverse of a matrix which is 100 billion by 100 billion, right? You would not be able to compute that, right? So that's why for those problems, we can only use first order method. The other advantage of first order method compared with second order method is it is compatible with GPUs. Why is that? Because first order method only uses matrix vector multiplication, right? And if you have a second order method, you need to take matrix inverse. So matrix vector multiplication is very easy to parallelize, right? It's probably the most naive thing to parallelize, right? But matrix inverse cannot be parallelized very easily, right? So the advantage of GPU compared with CPU is in parallelization, right? You can think about, there are some analogy people have made. You can think about if you have a lot of money, if you buy a GPU, it's like buying 10,000 bikes to help you deliver your products. If you buy a CPU, it's like buying one single Ferrari. Right? So which one is faster? That depends on the problem. Right? If your problem is serial or sequential, you would just buy a Ferrari because you can only do the next task after the first task is done. If your problem is very naively parallelizable, like matrix vector multiplication, or essentially all the first order method only use matrix vector multiplication, then this algorithm will run pretty fast on GPUs. Okay. Now, having said that, a second order method can be too expensive. There are something in between first order method and second order method called Cauchy-Newton method, where instead of computing the exact hashing, they come up with an approximate ways of computing the hashing, where the computational cost is reduced to n squared. Right? It's still slower than first order method, but then instead of n cubed, you can reduce the computational complexity to n squared per iteration. The idea of Cauchy-Newton method is to use an approximate hashing. Right? There are different ways to approximate hashing. Those methods are known as Cauchy-Newton method. These are probably the two well-known Cauchy-Newton method called BFGS and DFP. Both of these are named after the people who invented them. So in our homework, we will give you some exercise of Cauchy-Newton method. Then you could sort of derive that or implement that and see how it works, right? But then it will also affect the convergence property. The convergence is faster than first order method, but it's slower than second order method, right? That's as expected because the computational complexity is in between as well. Okay, so that's sort of all I want to talk about today. You can refer to, again, this convex optimization notes by Ryan Tipshrani and this convex optimization book.